Okay, so today we're going to talk about Gibbs free energy, entropy, and enthalpy. Let's start off with some definitions. What is Gibbs free energy? Well, we don't really know. The best way we can put it is it's a state function that relates enthalpy and entropy. Entropy is energy that is distributed or dispersed among the various motions of molecules of the system. Often it is the measure of randomness. Enthalpy is heat that is evolved or absorbed in the reaction, so heat exchange during the reaction. A spontaneous process is one that can go forward or continue without the need of any outside energy. So let's look at some of the units and the signs and all the meanings. Gibbs free energy is in joules per mole, and whenever this value is positive, it is non-spontaneous at any temperatures. When it is negative, it's spontaneous at all temperatures. Delta H for enthalpy is measured in kilojoules per mole. When this value is positive, the reaction is endothermic. When it's negative, it's exothermic. Entropy is measured in joules per mole Kelvin. Now, when this value is positive, there is an increase in entropy, or an increase in disorder. When this value is negative, there's more order. So let's do a practice problem. Here's the state function I was telling you about earlier. Delta G is equal to delta H minus T delta S. Now, if we take a look at our reaction, nitrogen gas plus oxygen gas yields 2 nitrogen monoxide. This occurs at STP, and we need to find the Gibbs free energy. Well, first we need to find delta H and our delta S value. To do this, we have to look at our reference tables. So for delta H, we look at our reference tables and find the enthalpy values for N2, O2, and nitrogen monoxide. Well, we know that N2 and O2 are in their standard states, so both their values are 0. NO happens to be 90.37 kilojoules per mole. Now, when you calculate the total enthalpy change, you do enthalpy of the products minus enthalpy of reactants. And because there are 2 moles of nitrogen monoxide, you have to multiply this number by 2. So your total enthalpy change would be 180.74 kilojoules per mole. Over to the entropy. You also use your reference tables. N2 is 191.5 kilojoules per mole Kelvin. NO2, 205. And you look up all the values and you do the same thing, products minus reactants. And when you do that, you get 84.47 joules per mole Kelvin. Right, now that we have our delta H and our delta S value, we need to convert our delta S value to kilojoules per mole. And we do this by moving the decimal place over 3 places to the left. So this is our new value. We said before it was at this reaction occurred at STP, so STP is 298 Kelvin. So we plug all these numbers into our equation. We get delta G naught is equal to 180.74 minus 298 times 0.04084474. And this equals 155.49 kilojoules per mole. And like we said earlier, because this value is positive, we know that this reaction at STP is non-spontaneous. Let's do another problem. We also know that delta G is equal to negative R constant times the temperature times the natural log of your equilibrium constant. So, for example, if we take the Haber-Bosch process, N2 plus 3H2 is at equilibrium with 2NH3. This is allowed to reach equilibrium at 333 Kelvin. So we have all of our numbers. We know that delta G is equal to negative, well, if we use the right R value, 8.314 joules per mole Kelvin times 333 Kelvin times the natural log of 1. Now we know our K value is 1 because our reaction has reached equilibrium. Now the natural log of 1 is 0. So 0 times all the other numbers will just give you 0. So we know that at any equilibrium, delta G is always 0.